now that we've done the homogeneous function and find out what its substitution would be, let's look at what we call a Bernoulli's equation. The Bernoulli brothers were pretty prolific mathematicians who did a lot of research into calculus. And so this equation, I assume, came from them, or it was written for them. Not for them, but named after them. But this is a situation where we have dy dx plus p of x times y equals f of x y to the n. So this looks a lot like linear. It looks like almost linear. If you look at the left-hand side of the equation, we have dy dx plus p of x times y. That looks very linear. But then we end up with this f of x times y to a power. So it's no longer a linear function, but it still can be solved with doing some substitution. We are going to assume that n is not 0, and we're going to assume that n is not 1. Because if n was 0, we're linear, in which case we don't need to do this. And if n equals 1, we can actually make it into linear by bringing the f of x times y to the other side, factor out the y, and then you get a linear equation. So in both cases, those would make linear. We don't want that. We are going to let u equal y to the n minus 1. And that's going to be the substitution we're going to do with this. All right, so let's go ahead and do an example of this. Let's solve x dy dx minus 1 plus xy equals xy squared. So the first thing to remember is you can't have an x in front of, you can't have anything in front of the dy dx besides 1. So we need to make this be a 1 in front of there. So the very first thing we'll do is divide through by x. So we have dy dx minus 1 plus x over x times y is equal to just y squared. This is not linear because even though the 1 plus x over x doesn't have a factor of y in it, the y squared, excuse me, the y squared is a y squared, and we can't get that any way out of that. So this is a Bernoulli because it is of the sort of the form of being a linear until we get to this y squared. So this is the Bernoulli equation. In this case, my n equals 2 because we have a 2 over here. We are then going to do the substitution. We're going to let, and I'm actually going to write the word let. We're going to let u equal y to the 1 minus n. In this case, n is 2. So we end up with that u is equal to y to the minus 1, which means y is equal to u to the minus 1. All right, so then we need to replace, if we're going to let y equal u to the minus 1, we need to think about taking the derivative of y with respect to x and what that's equal to. So remember, the derivative of y with respect to x is going to equal the derivative of y with respect to u times the derivative of u with respect to x. We're basically using the chain rule here. So we're going to have the derivative of y with respect to u is minus u to the minus 2 times du dx. All right, so now we can go ahead and do the substitutions we have. So dy dx is minus u minus to the minus 2 du dx minus 1 plus x over x times y, but y, remember, was u to the minus 1. And y squared would be y is u to the minus 1, so that'd be u to the minus 2. All right. So now let's see what this will give us. This doesn't look very good at the moment, but again, we don't like having anything in front of the du dx in this case. So we're going to divide through, or multiply through in this case, negative u squared. So we'll multiply every single term through by negative u squared, which gives me du dx plus 1 plus x over x. U to the negative 1 times u squared is u. And then u to the negative 1, we just get a minus 1 when we multiply through by negative u squared. Okay, so now what I notice is this is linear. So the homogeneous produced a separable equation. This Bernoulli, with this substitution, will produce a linear equation. So since it's linear, we can solve this using the integrating factor. So remember, the integrating factor is e to the integral of p of x. P of x is the 1 plus x over x dx this case. And the integral of 1 plus x dx is equal to the e to the natural log of x times x. Oh, plus x, sorry, not times x, plus x. Which would be e to the natural log of x, which is x, times e to the x. So we get x e to the x as our answer there. That's our integrating factor. Multiply that through x e to the x times du dx plus x e to the x times 1 plus x over x times u is equal to minus x e to the x. Again, with the linear function, these two terms together is your derivative with respect to x of your integrating factor x e to the x times u. So this is, we just take the integral of both sides. So we take the integral of the left-hand side, the integral of the right-hand side. And when I do the integral of a derivative, I just get the thing inside. So this is x e to the x times u. And the integral of minus x e to the x is minus x minus 1 e to the x plus c. Again, find that any way you want. Table of integrals, calculator, CAS, anything that works. Now, I want to get u by itself, so I'll divide through by x e to the x. So I'm going to get minus x minus 1 over x. The e to the x's cancel, plus c over x e to the x. Now remember, that's what u is equal to. I don't want u, I want y. Remember, u is equal to y to the minus 1. So I'm actually going to do something a little bit with this. I'm going to, well, I'll leave it this way. I'm now going to flip this upside down. So I'm going to flip the y upside down, 1 over y, in which case I flip this whole side upside down. And it's not slipping each individual piece, it's put the whole side under 1. So we've got minus the quantity x minus 1 over x plus c over x e to the x. Oops, I just realized I divided through by e to the x, and I wrote this as e to the x, should be e to the negative x. Okay, if you want to, you can do some other work on this. You can try to simplify this more. I'm sure that you can do some more algebra on this. One more type is a reduction to separation of variables. So if we have a dy dx equals some function of ax plus by plus c, we're going to let u equal that ax plus by plus c. And we do the substitution, and we'll show you kind of what we mean by this. This isn't one I can actually show you in general. It's just we would do this kind of substitution. So in this case, we have dy dx equals the tangent squared of x plus y. And I would like to be able to solve this in whatever fashion I can. So we're going to let, in this case, we're going to let u equal x plus y. And so that means du dx is, well, the derivative of x is 1, and the derivative of y is dy dx. So that means I can get the dy dx by itself. That's going to be du dx minus 1. So dy dx is du dx minus 1 tangent squared of u. So we have in this form, it doesn't look all that great at the moment, but we notice that we actually have I'd like to get the du dx by itself. So du dx is equal to tangent squared of u plus 1. And I notice now this is separable. So this is why this is called reduction to separation of variables, is when you do these kind of substitutions. And it's very specific. You have it in this form, you can do this substitution and get a separation of variables. So we now have du over tangent squared u plus 1 is equal to dx. And then we just define that integral. And well, actually, I wouldn't do that because that's really ugly. So let's actually do something slightly different. So that's what you think we can do, is it looks like it's separable, but it gets really kind of ugly looking. But if you think about it, if du dx is equal to tangent squared of u plus 1, then that means that tangent squared plus 1 is a wonderful trig identity. It's secant squared. So tangent squared plus 1 is secant squared. And then we can do the separation of variables. So now we have du over secant squared of u is equal to dx. This is actually cosine squared. Remember, 1 over secant is cosine, so we get cosine squared of u. Du equals dx. And then you just take the integral of both sides. So the integral of cosine squared of u du is the sine of u cosine u over top of 2 plus u over 2. And the integral of dx is just x. And then you can do your substitution back in. And once you do your substitution back in, you're done. So then we'd have sine, let's do the 1/2 out front. Sine of x plus y, cosine of x plus y, because remember that's what we let u be, plus, I'm going to do the 1/2 out front. So we'll do the 1/2, and then u was x plus y equals x. And so again, you can do some simplifying. I forgot my plus c, so you'd also have a plus c here. So you can go ahead and solve this if you need to and simplify it. And so this is a very specific one. It depends on which ones you have of what kind of separation you would do.